Okay, so let's look at 15.5, which is this is some applications of the integral. So perhaps you remember from maybe just do this the focus. Sorry. You may possibly remember from calculus 1, actually, that one of the applications was mass, computing the total mass of a length of wire, and so this was let's suppose that we have some delta, which is density. And if we had a length of wire, right, and x measured the position along the wire, and delta was really a function of x, then the mass of the piece of wire was the integral of the density, right? Where a and b are basically where the wire starts and where the wire ends, right? This was linear density, so this would be, maybe in grams per centimeter, or maybe kilograms per meter, or something like that. It's units of mass per units of length. All right, so that's in one variable. If we look at two variables, well, basically it's the same thing, right? If we now have density, but now it's a function of x and y, because if we're in 2 dimensions, and we have some region D, maybe that's not the greatest depiction of a region, but we have some region in the plane, and now the density is maybe grams per centimeter squared. Now, one place where this would this would come in, where it's maybe not units of mass, but it would be maybe density of people. Maybe it could be, number of people per unit area, or some other density. It could be charge, charge density. So anyway, let's just think about mass. So maybe in grams per centimeter squared, or maybe kilograms per meter squared, or maybe tons per kilometer squared. Then the total mass of this region. So total mass of maybe a plate that has a thin plate that has density given by delta is just again the integral of the density with respect to area. Now, maybe to point out something that you can probably see in the units already. Over here, so what do you have? I mean, what is the integral? Integral is a sum of a whole bunch of things, that are under the integral, right? So it's a whole, sum of a whole bunch of deltas times dx. Now, delta, if it's in the units grams per centimeter, and dx, well, that's that's the change, infinitesimal change in length. So that's in the units of centimeters. So this is grams per centimeter times centimeter. This is in the units of grams, which is what the mass should be. Same in here. We have delta is in the units of grams per centimeter squared. We're multiplying by area. That's presumably, in this case, in the units of centimeters squared, right? So that means that grams per centimeter squared times centimeters squared is in the units of grams, so it's unit of mass, right? That's why we're getting mass. So the units work out. And, in the same way, if we're in 3 space, right? We have some object in 3-dimensional space called W, then its mass is the integral over W of delta, just like before. It's the same thing. Here the units would be maybe grams per centimeters cubed, right? It should be units of mass per units of volume, right? Again, it's going to be in grams per centimeters cubed times centimeters cubed. This is going to be in grams, right? So this is the way that you would figure out the mass of something. That's even if the density is not uniform, right? So, for example, if you had like either it would be mass, so it could be some object made out of material that is not of uniform density, or maybe it's maybe it could be a plate. Maybe it is uniform density, but it's different thickness at different places, right? So you could think of the thickness as giving you the density in terms of area, right? So okay. So let's compute sort of an example, and it's going to look more complicated than it actually in the end really is. So suppose that we have, W is spherical shell between radii 1 and 2. That means it's this it's a big ball of radius 2 with a little ball of radius 1 cut out, right? It's the thing in between the radius 1 and radius 2, right? So let's suppose W is of density, and let's not give units here. It's in whatever units we'd use, as long as we use consistent units. Let's suppose it's of density 1 over R. I have to write it first like this: x squared plus y squared plus z squared, right? Which is really 1 over r squared. It's where r is the distance from the origin. So, sorry, I think I called it rho last time. Sometimes it's called r. So, rho. So, let's compute the mass of this, right? So really what we're doing is we're saying, mass is the triple integral. This is what we really want to compute. Except that looks really ugly, right? But we can compute this using spherical coordinates, just like we talked about last time. And it becomes quite easy. I mean, this is 1 over rho squared, right? So this is really 1 over rho squared dv. I just need to write down what dv is in terms of spherical coordinates, write down what how to describe w in terms of spherical coordinates as an iterated integral, right? So it's a triple integral. I'm going to have 1 over rho squared in the middle, then dv, well, this is rho squared sine of phi, if you remember from last time, and then the d rho, d theta, d phi. So let's write them, let's say, in that order: d rho, d theta, d phi. And that actually works because this really is a you know, what I think last time I called that a spherical box, right? So phi, we're looking at all the different phis. So phis go from 0 to pi, right? Theta, again, theta, we were going over all possible thetas, so 0 to 2 pi, right? And rho, well, it's the radii between 1 and 2, so 1 and 2, right? Now here, conveniently, the rho cancels out, and so this cancels out. If you think about it now, the integral in terms of rho, this is giving us 1, right? It's the integral from 1 to 2, and there's nothing here that depends on rho. Similarly for theta, there's nothing here that depends on theta, but that's giving us 2 pi. So this is really 2 pi times the integral from 0 to pi of sine phi d phi, right? And I'll let you compute this. This is 4 pi, right? So, and again, this is looks much more complicated than it is. But once we write it in spherical coordinates, it's actually quite simple. All right. So let's look at another related application of this. Now we can compute mass. So if we can compute mass, we can actually compute the center of mass, which is really what it is. It's the weighted average of the position variables, and it's weighted with respect to density, right? So what is center of mass of W with density delta? What is that? Well, it's x, let's write this, x sub cm, y sub cm, and z sub cm, right? It's some point, right? And we have that x sub cm is equal to, what's the average? So we're doing, if it's, if it was average with respect to volume, we do 1 over volume. This is going to be average with respect to mass. So we're summing up over W, and we're averaging X, and we're averaging with respect to mass. So mass is given by the density times dV, right? So that's at least the x coordinate. Then y coordinate is the same thing. And so is the z coordinate. Let me write it here. All right. Now, what would be, this center of mass? Where would that be useful? Well, it could be, for example, if you're doing, if you're talking about an object in space, for example, and you're trying to figure out, basically talk about its position, and maybe it's sort of, just going somewhere, rotating about. It's going to be basically, you can treat it as a point in space, and that point is its center of mass. So you can forget that it's a complicated object, and you can just think about its center of mass, and you can, that's basically going to be a position of that object, and maybe then you start thinking about gravity, how to several different objects interact with each other. All right, so that's basically what this is, and heard this before, right? I mean, if you have a a car will handle well in turns, tight turns, if it has a low center of mass, right? So this is because basically then it's sitting closer to the road. It's harder to tip it over. So it's important to be able to compute this quantity, right? So let's compute it with for a certain example, right? Suppose that we have suppose W is an eighth of unit ball, which we'll describe as it's by unit ball I mean the ball of radius 1. So this is all the points with that are less than equal to 1 in distance from the origin, and such that we're in the positive octant, right? So this is basically just this, if you'd look at this piece of the ball, right? That if you cut off every everything except the part that's lying in the positive octant, right? So cut a ball into 8 equal pieces, and we have and that's what it is, right? So let's suppose that we have this ball. Suppose that this is going to be uniform density. So let's just say the density is 1. That's basically, we can just ignore the delta in these formulas, right? So find center of mass. So for example, if you'd had such an object traveling through space, what point would it be sort of rotating about, or what point could you make it as, if you were to treat it as a single point, right? Or if you have it standing on your desk, you want to tip it over, and you want to say, well, when is it going to tip over? Okay, well, so the first thing that we notice is the symmetry of the thing. I mean, if I would change the variables, if I'd say this is x and this is y and this is z, it would be exactly the same problem, right? And the same thing as if I made this x, this y, this z, right? It doesn't really matter how we named our variables. So this by the symmetry of the thing. So by symmetry, we have that and if you think about it, a little bit more about, if you write down what it is, you'll see that it has to be the same thing, right? I mean, we have if we have let's say xcm. So what is xcm? Well, it's 1 over mass, right? And what is mass? I mean, we have the head mass before. Here it's just it's really just the volume, right? And times the integral of x dv, right? And again, it doesn't really matter how I cut this up, how I integrate. If I and how I rename my variables. So this should be the same as YCM, ZCM. So if I compute just one of them, I'm good, right? So let's compute the x coordinate, right? Well, let's compute the different, the two different integrals. We have maybe put it here. Let's compute just the volume, or the mass in this case, because the density is 1. And well, we have to figure out how to parameterize this object, right? So we will have rho squared sine phi d rho d theta d phi. Again, this is a spherical box, so I can put these in any order that I want. So maybe like this. So phi, in this case, well, it doesn't go over all the phi's, right? Because it only goes through half of them, right? It goes from 0 to pi over 2, right? If you think about how this looks, right? Because it's not going over anything in the lower half of the ball, right? I mean, that's cut off. That's not in W. In theta, well, it's kind of the same thing. Theta actually now is going only through a quarter of all the possible thetas, right? Because if I go through the first quarter, that's in W, but the second quarter isn't, the third quarter isn't, fourth quarter isn't. Alright, so that means it's also going from 0 to pi over 2. And the rho is going from 0 to 1, right? Now, we've done a whole bunch of these integrals, so let me just tell you what the answer is. It's like you have the integral from 0 to 1 of rho squared d rho is going to be 1/2, and then then you're going to have this integral of the phi is going to be a 2, and so on. Sorry, not a 2, because it's pi over 2. Anyway, you're gonna get in the end pi over 6, right? If you do this integral, right? So it's an exercise left to student, right? Now let's do the other one. So if we have the other integral is x dv, right? So again, we can think of the iterated integral in the same way, right? So we're gonna in the same way we're gonna parameterize phi and theta, right, and rho. But now we have to put in x, right? So what is x, right? X is well, it becomes a little bit more complicated, right? We're gonna get rho sine phi cosine theta. That's x, right? This thing, that's my x coming from over here, right? And then I have dv, and that's the rho squared sine phi d rho d theta d phi, right? This is the dv. All right. Now, if we put this thing, put these things together as much as we can, simplify. We have, again, it's a product of a function of rho, a function of phi, and a function of theta, right? There's really, let's start with the rho. Why not? So it's the, I get an integral from 0 to 1 rho cubed, right? D rho times, let's maybe then go to phi, why not? And it's going to be the integral from 0 to pi over 2 of sine squared phi, right? I get one sine out of here, one sine phi out of here, the phi, and times the integral from the derivative pi over 2 of, and now the only thing that's left is the cosine. All right. Now this is 1/4. That's an easy one. Then let's see which one is the next one. Is the phi? You can check that this is pi over 4, and this is you use you again use trigonometric identity to rewrite the square, right? But I'll leave that up to you. I mean, this is just calculus 2, right? And finally, we get what do we get out of the cosine? We actually get 1, right, over here. So this is pi over 16, right? So what is my, running out of room a little bit, xcm, which is it's going to be the ycm and the zcm, right? So what is this? Well, this is well, I'm going to have this integral, so pi over 16 divided by this, so pi over 6, so it's 6/16, or it's 3/8, right? So the center, let me write it here, center of gravity of W is 3/8. All right. So that's that's the center of mass. Now, it's sometimes you would call this, what we actually computed was a centroid, because we assumed uniform density. So if you let delta, right here, if delta is 1, and if we just assume it's not really there, it's just an average of the position over the volume, then this is a centroid rather than a center of mass. But it happens to be the same thing if the density is uniform. If the density is not uniform, then it's not going to be the same thing. It's just, for a centroid, you don't put the delta in. That's the only difference. So, all right. So this is these are all the applications that we're going to look at, just to get something to think about, right? All right. So see you next time.